So, let us get started with a few other technicalities, and the first point would be the Jacobians and the Hessians. So, we have an approximating function which depends upon the weight, the synaptic weights of the multilayer perceptron and the input data samples, and we would like to take the partial derivative of this approximating function, which is a function of both the synaptic weights and the input data points with respect to the synaptic weights, and that gives us the Jacobian matrix. So, let us kind of formalize this. Let W denote the total number of free parameters, that is the synaptic weights and biases of a multilayer perceptron to form a vector, and we call this W bar. So, this should not be confused with the total number of free parameters. Maybe I can call this some other number, but we will use this as W. Okay. So, but you may actually question why we need to deal with Jacobians and Hessians. If we formulate the Jacobian matrix, any rank deficiency in the Jacobian matrix can cause the backpropagation algorithm to obtain only partial information of possible search directions during gradient descent, and this can lead to longer training times. Right. From the performance of the algorithm, we are interested in learning about the Jacobians. So, with this formalism that we have, let us continue to define a few other variables. Let capital N denote the examples presented to the network. As we learnt, using the backpropagation algorithm, we can get the approximating function f, which is capital F. So, I use small f for the true function and capital F for the approximating function. The approximating function is a function of the synaptic weights, which is W bar, and then these inputs x. Right. I can put this as a set, indicating that you have learnt the examples. Now, suppose we have this set of data points xn from small n equal to 1 to capital N. If I am doing stochastic learning or online learning, every time at every time step small n, I am presenting a data vector x. So, that is the index that I have here, and this forms this set. Okay. Now, I compute This matrix, which is called the Jacobian matrix, defined as follows. It is a partial of the approximating function and the data point at time n with respect to the weight w I j. I will define what the indices I and j are in the subscript. I goes from 1 to capital W, which is the total number of free parameters, and j goes from 1 to capital N, which is the number of examples. Now, empirically, the rank of this matrix can decide the efficiency of the backpropagation algorithm, and in particular if j is not full rank, and if it is not full rank, that means it is rank deficient, and this would lead to longer learning times. Because it can cause the algorithm to search in different directions and not align. So, therefore, you may not get a converging solution. So, therefore, this is one of the important technical aspects. Similarly, we have the Hessians. The Hessian matrix is basically the second order derivative of the cost function, which is a function of the weight. Now, why do we have to study Hessians? Why do we need to study Hessians? Because this has a sort of second order effect. The eigenvalues of Hessian have a role in the backpropagation dynamics. The inverse of the Hessian provides a basis for pruning and deleting the insignificant weights, because you do an eigen decomposition on this inverse matrix, and then using the eigen modes you can figure out how to prune insignificant weights, and this can lend itself to second order optimization methods. So, sort of to summarize, eigenvalues of Hessian have a role in the backpropagation algorithm dynamics. Because inverse of the Hessian matrix can provide a basis for pruning or deleting insignificant weights. In some sense, these are dead neurons, and if the weights are not really helpful for us, we may want to kind of remove these dead neurons in our network, and in that sense we are having reduced complexity in terms of space, possibly also in terms of computation. And a direct consequence of this study would be that the approach can lead to second order optimization methods. If you think about the backpropagation algorithm, all we do is take the gradient, right? We have the local gradients and then we do a synaptic adaptation based on the local gradients. It is basically taking the derivative, it is just a first order effect. But if we want to have second order effects, then we need to look into Hessians and some of these other technicalities and then think about having a more optimized network based upon these objects that we have, Jacobians and Hessians. Okay. There is another technicality to deal with Hessians. The Hessian of an error surface can have certain number of eigenvalues, right. It can typically, I would say this is more an empirical result, has the Hessian of an error surface empirically has a small number of small and large sized eigenvalues, and it has a large number of medium sized eigenvalues whose compositions are influenced by the data, right. The exact distribution of these eigenvalues, they depend upon some parametrics such as the non-zero mean, in the input signals, and also the induced neural output signals that can have biases, right, which are also non-zero. There could be correlations between various attributes of a data vector. Last but not the least, there could be wide variations in the second order derivatives of the cost with respect to the weights from one layer to the other, right. There can be a sort of a learning dynamics, right. The output layer learns faster than the hidden layer, and as you propagate the errors across various layers, there can be dynamics as to how the learning mechanism can be. And why are these eigenvalues important? From our linear dynamical systems, we know that the behavior of a system, right. If you think about an LTI system, a linear time invariant system, and you look at the eigenmodes of the system, right. You look at the homogeneous difference equation or differential equation, and you look into the roots of that equation, right. The largest eigenvalue will decide the behavior of the system, right. I give you two eigenmodes, one is 2 and other is say 0.5. The growth rate of the sequence or the response of the system behaves dominated by the largest eigenvalue, right. The largest eigenvalue dominates the system behavior. So, therefore, it is very important to study the distribution of the eigenvalues of this matrix, and that is the reason if we know the distribution of the eigenvalues which are influenced by non-zero biases within the input signals and the neural induced output signals, correlations between data elements, etc., right. This can help us to invoke second order optimization techniques for accelerated convergence, right. All the techniques that you have learned so far are based upon the gradient, but if we invoke the Hessian, we can kind of bring in accelerated convergence, and that is sort of an idea that we can get using the Hessians. Okay. The next topic would be complexity regularization. So, the first and foremost thing that comes into our mind when we think about learning networks are that they are essentially statistical in nature, right. If you think about a neural network design, it is basically a statistical engine. It depends on the data points and it is governed by certain dynamics of the optimization function that you start with. And we discussed gradient based ideas. We also discussed a few technicalities dealing with the Jacobians and the Hessians and how the second order optimization techniques can help us better in terms of accelerated convergence. One of the important aspects of network design or a neural network design, particularly in our context it is a neural network design, is how optimal are we in terms of the network complexity. This is very important because when we think about data, two things come into our mind. One, the complexity of the network. Second, the learning aspects of the network, right. We want to have an accelerated learning time. At the same time, we want to have fewer number of parameters, because if the network gets complicated, then it leads itself to increased space and time complexities. And if we think about implementation into a system, maybe a hardware system, a neuromorphic system, etc., then we have troubles. Okay. So, let us discuss the idea of complexity regularization and what is the basic idea behind this. Now, in the context of the back propagation algorithm, we may want to minimize the following risk function. The risk R as a function of the network parameters is broken down into two components. One is the average error as a function of the weights. This is basically the standard performance metric. In addition to that, we have the script E suffix C as a function of weights, and I call this the complexity part of the risk, and we have a scalar parameter lambda that we would like to introduce that controls the trade off between how we can optimize these two quantities, right. When lambda is 0, then we pay our entire attention to the standard performance metric, which is the actual performance function, the square error or cross entropy or whatever metric that you have. So far we considered the square error because we looked at the error at the output of each neuron in the output layer, right. We have neurons in the output layer and we consider the output of the neurons in the output layer, right, and then we formulated the error signal and we look at the square error, and that is our performance metric, and this is a standard performance metric. We can also have the complexity part where we want to kind of strike a trade off. When lambda equals 1, everything is in terms of complexity, right, and this does not make any sense because if you want to have really a low complex network, you do not have you do not need anything, right, maybe just a single neuron as a function of weight. What would you want, right, but you want to have both of these two functionals, that is the standard performance metric and the complexity metric, and then you want to kind of strike a trade off between these two metrics that you want to get a right balance. Now EC of W is the complexity penalty measured in terms of the network weights W. One example for EC of W could be this norm square of the weights, right, and if we choose a certain threshold or we strike a balance in choosing the minimum over all weights of this complexity functional, then we can force some weights to 0 and permit larger weights. So in that sense we are kind of pruning some of these weights that have no significance to the performance of the network, or dead neurons can be sort of weeded out. So you may question, how do I choose this functional, right? It really is a choice, like in any optimization game, right, in any optimization formalism, what you want to optimize depends upon what you start with. So you can choose, this can be a meaningful metric, choice of the square of the norm of the weights can be a meaningful choice. You can have other choices of the optimization metric, but I think what is very important in this regularization, lambda is the scalar which kind of, right, lambda acts as a regularizing parameter which strikes a trade off between the standard performance metric and the complexity part, and then by using a suitable choice of the complexity functional you can kind of optimize the network further, right. This completes the idea behind complexity regularization. So let us discuss some alternative strategies for learning based upon the second order update. So far we have been qualitative, right, more at the conceptual level. We discussed why Hessians are important, why the Jacobians are important, but we never expanded the performance function which is a function of these weights in terms of second and higher order terms, to see the influence of how the learning can be influenced by an appropriate choice of second order methods in the expansion of the performance function. Okay. So, let us start by expanding the performance function, which is our square error. Let us begin by expanding the performance function, which is E average of W plus delta W through a Taylor series. So, this can be written as follows. So, this is the function at the weight vector W, then you have the gradient of the weights over a small perturbation, delta W plus 1 upon 2 factorial delta W transpose the Hessian times delta W plus higher order terms. Right? We can think about this expansion as a small perturbation delta W around this weight vector W. So, one of the direct ways of dealing with this problem would be how to choose this optimum delta W, right. So, for which we can set the partial of this quantity, which is W plus delta W, partial of the error that you have evaluated at W plus delta W with respect to delta W, and we can equate this to 0, right. By doing standard matrix calculus, we can land up with a solution which is of the form minus H inverse G, right. So, this is a matrix. So, I will write this in bold, and this is a gradient and this is a vector, right. So, the optimum delta W that you want to choose can be related to the Hessian matrix according to this equation that we have here. This is how we can have a differential weight update based upon the second order statistic. This is the second order statistic, which is based upon the Hessian, and we can have other higher orders. If we can invoke higher order statistics if we want to have a better approximation to the performance surface in terms of the perturbation, and this can lead us into alternative strategies towards learning based upon higher order statistics. But in practice we stick to second order statistics because it is easy to control the second order computations. It is easier to control the performance when we deal with second order statistics, hence we stick to just second order statistics, and based on that we get the modified update rule. There is also an algorithm called the optimum brain surgeon algorithm. The name seems to be interesting and fancied. So, the idea is pretty simple. So, because we want to optimize over delta W, that is we want to minimize over this vector delta W of this function 1/2 delta W transpose the Hessian matrix times delta W. So, what we can do is we can follow a 2-level optimization strategy here. We can minimize over the synaptic weight vectors that remain after the ith weight vector is set to 0. So, we set the ith component of delta W to 0 and we minimize over all the weight vectors that remain after this component is set to 0, right. We set this ith component to 0 and minimize over all synaptic weight vectors that remain after this setup is done, and we do this minimization again over that particular choice of index I, right. We minimize again over, I would say, all indices I to figure out what is the best way that we can get delta W, because it is a 2-step optimization process. So, I set one of the components to 0 and then optimize over the rest, and then I do this over all the other components. In that way I figure out what is the right component, what is the right index I and what is the right synaptic weight vector that remains after that, right. This is one of the algorithms based upon the Hessian to update the differential of this weight vector that can be useful for our update in the backpropagation algorithm for the delta rule based upon the Hessian. Okay. So, this summarizes the strategies for learning. We basically derived the backpropagation algorithm from first principles in our earlier lecture, and that was based upon the gradient. Then we looked into two objects, mainly the Jacobians and the Hessians, and we saw why the Hessians were useful for us, right, because if we look at the inverse of the Hessian matrix, that has a role in terms of the eigen distribution, right. If you look at the eigenvalues and we want to keep those that are useful for us and prune out those that do not influence the performance of the system, right, and that way it can lead itself to complexity regularization in some sense. And we discussed how we can expand the performance function using higher order statistics. In particular, if we restrict ourselves to second order statistics, we expand the performance function up to the second order in the Taylor series expansion, and then we can solve for the optimum delta W based upon just simple ideas on matrix calculus. And if you want to adopt a 2-step optimization procedure, you can do using the optimum brain surgeon algorithm that I just described, right. So, with this I hope you will be able to construct your own performance metrics depending upon what level of approximation you need, and then derive the gradient rules and the optimization from first principles, and you can feed that into the algorithm, and the algorithm should basically work. But a small point of caution, unlike in signal processing, which are predominantly linear signal processing based techniques, where it boils down to doing some simple computation such as an inverse of some matrix times something, like for example the Wiener-Hopf solution is dependent on the autocorrelation matrix and the cross correlation vector, and then you can basically solve for your optimum weights in the mean square error sense, and you can think about various ways of optimization depending upon how you can make the computation of the inverse more efficient based upon techniques in numerical linear algebra, right. But in the case of nonlinear signal processing techniques, particularly in neural networks, it is much more than that. Your solution, by computing the gradient or the Hessian and then evaluation of the solution based upon some calculus, does not suffice, because we have all these network parameters and we have to invoke heuristics and certain update rules which are important for us. For example, the momentum learning rule was one such heuristic that we had, but it works very well, but that rule cannot be derived from first principles based upon the Taylor series of approximation to the performance function, right. So, these are all some of the important points that one has to bear in mind as we solve the problems, right. Hopefully, you would have found these tools to be helpful in your research or possibly in your work towards handling these data points. Having studied the MLP, it is important for us to figure out a strategy towards dividing our data set into training samples and then testing samples, and typically this is done using a strategy called the cross validation strategy. So, let me briefly motivate why we need this strategy. Let us imagine we have a pool of samples and we trained on this data set and possibly we had an overfitting. When we try this over a different data set, then we may not get good results because of this anomaly which is inherent because of various feature vector observations that we have across data sets, right. So, different data sets can lead to different feature vectors, which may lead to the ability of the neural network to not generalize so well. So, whatever it has trained on one particular data set, it may not be able to perform well on a different data set. So, for this purpose we follow this strategy called cross validation. Typically there are two modes. One is a leave one out strategy. So, in this case imagine you have n samples, we train on n minus 1 samples and test on the other. So, we do this for n choose 1 choices, and this is feasible because n choose 1 is n. So, therefore, it is at least in the order of n over the number of samples, but if you choose k out of these n samples and then test on n minus k, then n choose k can be quite large if n is large and also k being large, right. It becomes a combinatorially difficult problem to tackle. Another alternative towards cross validation is this k-fold cross validation. So, we have n samples, we divide the n samples into k equal groups, we train the k minus 1 groups and then we test on the other and we repeat over all the choices of the groupings. So, this way every group would have been tested at least once. Okay. So, this is a sort of a I would say an empirical method in the absence of a rigorous theoretical setup as to how we can choose the data sets, how we partition the data set so that we can get guaranteed generalization ability through the learning network. Okay. So, this is a small detail that you will need to work so that your algorithms work well in practice. Okay, we will stop here.